All right, so here we go, beginning the final unit of our semester, which is on limits. So in this unit, we're going to talk about what a limit is and how to evaluate and some of the properties of limits. So let's start with this warm-up. Here I've got f of x equals x squared minus x plus 2, and I want to fill in the tables of values. So when we evaluate x equals 1.9, we find that f of x equals 3.7100, and I'd like for us to round to the nearest 10,000th, so that's 4 places. Plugging in 1.99, we have 3.9701, and plugging in 1.999, we have 3.9970. Plugging in 2.1, we have 4.3100. Plugging in 2.01, we have 4.0301. And plugging in 2.001, we have 4.0030. And then based off of this table of values, what can we conclude about f of 2? Let's take a look at what's happening. So 1.9 to 1.99 to 1.999, we're getting closer and closer to 2. Likewise, from 2.1 to 2.01 to 2.001, we're getting closer and closer to 2. Let's see what's going on with the function. Here we go 3.7, 3.97, 3.99. That's getting closer to 4. On the other side, we have 4.3, 4.03, 4.003. We're getting closer and closer to 4. So we can conclude, even though we haven't evaluated f of 2, we can conclude that as x approaches 2 from the positive side, or from the right-hand side, so that would be this table here, our function, f of x, approaches 4. And as x approaches 2 from the left-hand side, or from the negative side, f of x also approaches 4. So we can say, therefore, we can say f of 2 is equal to 4. And I'll put a little note there. That is only if f is continuous at x equals 2. And we'll talk about continuity a little bit later in these notes. But this is true if f is continuous at 2, which we know this is a quadratic, it's a polynomial, it is continuous across all real numbers. Okay, so let's define what is the definition for the limit. So we can say the limit of a function is some value L, that's capital L, that the function approaches as the input, usually it's a function of x, approaches some value a. And the notation that we use, we can say the limit, Lim, of f of x as x approaches a equals L. We would read that as the limit of f of x as x approaches a equals L. One thing that I want to note too, you can put a star next to this. We look at the function values that are close to x equals a, but not necessarily at a. So close to x equals a, but not necessarily f of a. So just returning to our warm-up, we're looking at the function values close to f of 2, right, where x equals 2. So we're getting closer and closer to 2 from either side, and we're analyzing the function values as we get closer and closer to that x value 2. Now, I've presented three different diagrams here. Here we've got a continuous function. It looks like a polynomial function. It's continuous, it's smooth here. This second example, we've got a function, it's continuous, it's smooth, but we've got a removable discontinuity here at x equals a. So we've got a removable discontinuity, or a hole in the function. And then the function value, f of a, is actually right here. So this point, we could say, is a f of a. So that point where the function is defined is not along this curve. We've got a hole. And then in this third diagram, we've got the same thing, but now we've got a hole here. And the function is actually not defined at x equals a. There is no point that the function hits at x equals a. Now, we're saying the limit is where the function approaches, what the function approaches as we get close to the x value. So looking at a, as we get close to a, what does our function approach? Well, it gets really close to L. Here, the function approaches L. Now, at a, the function is something else, but it appears as we get close to x equals a, the function approaches L. And likewise, the same thing happens here. As we get closer and closer to x equals a, the function gets closer and closer to L. So the truth is, the limit of f of x as x approaches a equals L in all three of these cases. So even though the function is defined elsewhere, if the function approaches another value, right, from either side, then the limit is that value. So in each of these three cases, the limit is the same. Let's try a few examples. Example 1 says estimate the limit of x minus 1 over x squared minus 1. And we're going to use a table of values. So let's go ahead and make that table of values x f of x. And I want to know the limit as x approaches 1. So I want to choose values that are really close to 1. So I'll start off with 0.9. We'll go to 0.99. We'll go to 0.999. We're getting closer and closer to 1. We'll do the same from the other side. So we'll go 1.1, 1.01, and 1.001. So we'll get closer and closer to 1 from the other side. When we evaluate the function at 0.9, we get rounded to 4 places. We have 0.5263. Evaluating at 0.99, we have 0.5025. Evaluating at 0.999, we have 0.5003. We have at 1.1, 0.4762. 1.01, we have 0.4975. And at 1.001, we have 0.4999. So looking at this table of values, we can conclude that the limit as x approaches 1 of x minus 1 over x squared minus 1 is about 0.5. We're getting closer and closer to 0.5000. So let's now talk about limits by direct substitution. This is another way that we can evaluate limits. So the definition for finding limits using direct substitution is if f is a polynomial or a rational function and a is in the domain of f. So it's not at undefined, it's not a vertical asymptote or anything like that. So a is in the domain of f. Then we can say that the limit as x approaches a of f of x is equal to f of a. It's just the function value at x equals a, as long as we're looking at a polynomial or rational function where a is in the domain. In other words, we can say that this is true for all functions that are continuous at x equals a. So the reason why we can say this is about polynomial or rational functions is because if these functions are defined at x equals a, they're also continuous by definition of each of these functions. So let's return actually back to example 1, but I want to solve this using direct substitution. I want to see if we can get that limit using direct substitution. So plugging in x equals a into our function. Now we're looking for the limit as x approaches 1. If we were to plug in 1 here, we would have in the denominator 1 squared minus 1. Well, that would be 0. So this would be undefined at x equals 1. So as it is right now, we cannot use direct substitution. We have to manipulate the equation somehow, the function somehow, in order to determine the limit. So I'm just going to rewrite the limit. We're going to say the limit as x approaches 1 of x minus 1 over x squared minus 1. Well, I notice that the denominator can be factored, right? We can say that this is the limit as x approaches 1 of x plus 1 and x minus 1. Also, when we are setting up a bunch of equalities, remember to carry over your limit, right? To only write limit once and say that this is equal to just this is not true. We need to also include the limit every single time we set something equal to it. So looking at this, I notice that we have an x minus 1 in both the numerator and denominator, so I can say that we've got the limit as x approaches 1 of these cancel. So we just have 1 over x plus 1. Now we can use direct substitution. So now we can substitute in x equals a or x equals 1 in for x. So we can say that the limit is equal to 1 over 1 plus 1, which is 1/2. So sometimes it requires a little bit of manipulation in order to use direct substitution. Let's take a look at example 2. Example 2 says, find the limit as x approaches 0 of 1 over x squared. So let's find a table of values. Let's write that out. We want the limit as x approaches 0. So we'll start off with, say, plus or minus 1. We can say plus or minus because we're squaring it. For both negative 1 and positive 1, f of x is the same. So we have 1 over 1 is 1. We can plug in 0.1, again, plus or minus. 1 over 0.1 squared is 100. We have 0.01. 1 over 0.01 squared is 10,000. And we'll go one more. We'll say plus or minus 0.001 is 1 million. So this grows very, very quickly as we get closer to 0. So let's graph this function. At positive 1, we have 1. At negative 1, we have 1. At 1/10, we have 100. So that's way up here. And as we get closer and closer to 0, it only gets bigger and bigger. But at x equals 10, right, we have 1 over 10 squared is 1/100th. So at x equals 10, we have 1/100th. It's very small. The shape of the graph curves upward as we approach 0. And it goes outward as we increase x, and it approaches 0. And the same is true for the function on the negative side. Draw on that curve. It goes all the way out here. So we can conclude that the limit of 1 over x squared as x approaches 0, right, it's just getting bigger and bigger, right? We also see that from our table of values. It's just getting bigger and bigger. Our limit is infinity. Now, definitely include this in your notes. This does not mean that the limit exists. In fact, the limit, if it equals infinity, right, the limit does not exist. And the reason why is infinity is not a numerical value. In order for a limit to exist, it must approach some numerical value L as x approaches a. That's the definition for a limit. The next thing that I want to talk about is one-sided limits. So we're going to start off with a left-hand limit. So a left-hand limit, you could probably guess it's the limit of a function, we'll say it's f of x, as x approaches a from the left-hand side, so from the negative side, or from the left-hand side. We're saying that's equal to just some limit. So we can evaluate a limit from just a single side, right? So as we approach a from the left-hand side, what does the function appear to be approaching? Likewise, the right-hand limit, you can probably guess, is the limit of f of x as x approaches a from the right-hand side or from the positive side. And we're saying that's equal to some value. Okay? One thing to know about left-hand and right-hand limits is that the limit of f of x as x approaches a, so this is just the general form for a limit, right? So notice that I haven't indicated either side. This implies both sides, right? So this implies that it's the limit from either side. We have that the limit equals L if and only if the left-hand limit, so the limit of f of x as x approaches a from the left-hand side, equals the right-hand limit, so the limit of f of x as x approaches a from the right-hand side, and both of those are equal to L. So we're saying that if the left-hand limit equals the right-hand limit, and that equals something, then the limit of the function at that x equals a is L. Okay? Anytime you see if and only if in math, that means pretty much equivalent statements. So we're saying that the limit equals L if and only if the right-hand and the left-hand limits are the same. Or if the right and left-hand limits are the same, then the limit is that limit L. So let's take a look at example 3. Here we have an electric current is switched on at time 0, and we're saying that the function is 1 if the electric current is on, and the function is 0 if the electric current is off. So they give us the piecewise function, and we want to find the limit as x approaches 0, or I should say as t approaches 0. So if we were to draw this, we would have that from t is greater than 0, the function would be equal to 1. Greater than or equal to 0. The function is equal to 1. So we have the straight line from 1 onward. But less than 0, it's going to be the function equals 0. So we've got this behavior here. And I want to see what's the limit as t approaches 0. So the limit of h of t as t approaches 0 from the right-hand side, well, if you look at this, we're coming in from the right-hand side. As we get closer and closer to 0, x equals 0, or t equals 0, what value do we get close to? We get really close to 1. And the limit of h of t as t approaches 0 from the left-hand side, so the left-hand limit, coming in following h, we get really close to 0, right? Our function approaches 0. So in this case, the limit of h of t as t approaches 0 from either side does not exist. It does not exist because the left-hand and right-hand limits do not agree. Let's take a look at example 4. So here I have g of x as a piecewise function, and I want to find the limit as x approaches 2 from the right-hand side. So we're going to look at x equals 2. We're going to see where does the function approach as we move into 2 from the right-hand side. Well, we're approaching 1. How about from the left-hand side? So from the left-hand side, we're coming in as we hit x equals 2. We are approaching 3. So what about the limit as x approaches 2? So we take a look at the left-hand and the right-hand limits. They do not agree, so therefore the limit does not exist, DNE. How about at 5, the right-hand limit? So at 5, the right-hand limit, we are approaching what appears to be 2, right? And as we're approaching 5 from the left-hand side, again, we're approaching 2. So then, because the left-hand limit and the right-hand limit agree, the limit of the function is 2. This is not to be confused with g of 5, which is 1, right? Where the function is defined is not necessarily equivalent to the limit of the function at that same x. A few more examples. So here we're trying to find the limit of this function as x approaches 0. We can try using direct substitution, but notice that when we plug in 0 for x, we've got 0 squared in the denominator. This is undefined at x equals 0. So we can't use direct substitution quite yet. We have to manipulate the function in some way. So I'm going to show you a trick, and this might be helpful. So we're going to be multiplying by the conjugate. So as a reminder, a conjugate, if you've got x plus y, its conjugate is x minus y, and vice versa. So I'm going to rewrite it. We've got the limit as x approaches 0 of the square root of x squared plus 9 minus 3 all over x squared. Well, we've got a square root minus 3, right? Its conjugate would be that same square root plus 3. So we have x squared plus 9 and then plus 3. Now, if we multiply the numerator by the root plus 3, then we have to also multiply the denominator by the same. So when multiplying this, we've got the limit as x approaches 0. Don't forget that. Well, we've got on the top, we've got this square root this would be x squared plus 9, and then this would become minus 9. So this is a difference of squares. And then in the denominator, we have x squared times square root of x squared plus 9 plus 3. Okay? In the numerator, we have a plus 9 and a minus 9 cancel out. And then we've also got an x squared and an x squared. So all that's left, so again, limit as x approaches 0. All that's left is 1 on the top. And then we've got the square root of x squared plus 9 plus 3. So now we can use direct substitution. So then, direct substitution. So we can say that the limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3, I'm just rewriting it. Plugging in 0, we have 1 over square root of 0 plus 9 plus 3. Square root of 0 plus 9 is the square root of 9. So we have 3 plus 3, which is 1/6. So the limit here is 1/6 as we approach 0. Let's take a look at some rational functions. So in order to graph this, I'm going to start by factoring this. I notice that the numerator, we can pull out a GCF of 5. So we have 5 times the quantity x minus 2. And the denominator, we can say x plus 5 and x minus 2. We can cancel out those x minus 2, so we have 5 over x plus 5. So this tells us we've got a vertical asymptote at x equals negative 5, so that would be right here. We've also got a removable discontinuity at what we cancel, that x equals 2. Let's see, if we were to find zeros, let's see, we don't have any zeros because we've got a horizontal asymptote at y equals 0, right? Because it's bottom heavy, right? Dominant term rule. Let's see. Let's draw that in. Okay, y-intercept, we plug in 0 for x, so we have 5 over 0 plus 5 is 5 over 5, or 1. If we were to plug in, I want to find out what the coordinates are for that hole. So if we were to plug in x equals 2, then we would have 5 over 2 plus 5 is 5/7. So that would be 2, 5/7. So that's right about here. the behavior near the asymptote, so as we approach -5 from the positive side, let's see, this would be positive quantity, so we're approaching infinity. So we get this behavior here. And as we approach -5 from the negative side, this would be negative, so we'd be approaching negative infinity. We've got a function that looks like this. It's a rational function, whole at 2, 5/7. Okay, so as we approach 0 from the negative side, we're getting closer and closer to 1. As we approach 0 from the positive side, we're getting closer and closer to 1. So the limit, because the left hand and right hand limits agree, our limit is 1. F of 0 is also 1. This is true because we've got a rational function that's continuous at x equals 0, so we can use direct substitution. That's by definition. At 2, well, 2 from the negative side, we're coming in from the negative side, from the left-hand side, it looks like it's approaching 5/7. And 2 from the positive side, we're approaching 5/7. So then the limit must be 5/7. These limits agree. However, f of 2, we've got a hole. It's undefined there. Okay? As x approaches negative infinity, so as we move to the left, our function gets really close to 0. It's approaching this horizontal asymptote. And on the right-hand side, again, we're approaching 0, that horizontal asymptote, as x approaches infinity. And then as we're approaching -5 from the left-hand side, so this is our vertical asymptote from the left-hand side, we're approaching negative infinity. And as we're approaching -5 from the positive side, so from the right-hand side, we're approaching positive infinity. As we're approaching -5, just in general, because these do not agree, this limit does not exist. And again, f of -5, that's undefined. We've got a vertical asymptote there. So is the graph continuous at -5? No, it's not. We've got an asymptote. F of -5 is undefined. And then what type of discontinuity does it have? It's a vertical asymptote. What about at 0? Is it continuous? It sure is. It follows along. It hits the axis, the y-axis. It is continuous. And in this case, the limit is equal to the function value. And then how about at x equals 2? Well, is it continuous? No. We've got a break in the graph. We can say that the factor x minus 2 is removed. So at x equals 2, there is a removable discontinuity. There is a removable discontinuity. And I'll sometimes refer to that as a hole in the graph. Let's try one last example. So here I've got this rational function. First thing I want to do is factor. I know that the numerator factors to x plus 2 and x minus 1, and the denominator is just x minus 2. So we've got a vertical asymptote at x equals 2. We've got zeros at -2 and +1. We've got a y-intercept of, let's see, plug in 0, we have 2. -1, so that would be -2, over -2, so that would be 1. We've got a y-intercept of 1. Okay. We also have that the degree of the numerator is 1 greater than the degree of the denominator. So we have a slant asymptote. Let's go ahead and divide that out. So we've got dividing out x minus 2 into trinomial x squared plus x minus 2. So we bring the first term down, we multiply, and we add. We multiply, and we add. So this would be 4. So then we could say that f of x is equal to x minus 2, what we divided out, times we have x plus 3 plus 4 divided by x minus 2. So then we have a slant asymptote at y equals x plus 3. That's that linear equation there. Okay. So let's go ahead and plot that. We've got y equals x plus 3, so here's 3. Slope is 1, so then we can have something that looks like this. Okay. Let's find another point on this side of the asymptote. So we've got, let's try f of 3. Let's find another point. So plugging in 3 for x, we have 3 plus 2 times 3 minus 1 all over 3 minus 2. So that would be 5 times 3 minus 1 is 2. 3 minus 2 is 1. So we have 10. So we have the point 310. Let's go ahead and plot that. That's up here. Okay. So to sketch the curve, we've got this here. Okay. All right. So as x approaches 0 from the negative side, we are getting close to 1. As we approach from the right-hand side, we're also getting close to 1. So the left-hand and right-hand limits agree, so our limit is 1. F of 0 is defined, so it's defined at 1. At negative, or at 1 from the left-hand side, so we're coming in right here. From the left-hand side, we're approaching 0. From the right-hand side, we're approaching x equals 1, f equals 0. And then the left-hand and right-hand limits agree, and the function is defined. As we approach negative infinity, so as we move to the left, our function blows off to negative infinity. And for positive infinity, we're blowing off to positive infinity, so our function approaches infinity. Approaching 2 from the left-hand side, well, our function is going downward, so we're approaching negative infinity. Approaching 2 from the right-hand side, our function is going upward, so we're approaching infinity. And so because the left-hand and right-hand limits do not agree, the limit of the function does not exist at 2, and neither does the function. The function is undefined. We've got a vertical asymptote at x equals 2. Okay. So this is our final unit on limits. Go ahead and try the homework, get a lot of practice, study up, and have a great day.